Lab 3, black hole in orbits. The purpose of this lab is to investigate the motion of objects in orbit, and to do this we're using Newton's second law. As a preview of the main results, the mass of the black hole was found by setting the net force equal to the gravitational force. It's really difficult to create a stable 8-figure orbit for the second part, and that overall computer models are useful for analyzing the motion properties of objects in space that otherwise can't be measured directly. So the main model used was the momentum principle in Newton's second law, which says that the net force is equal to the rate of change of momentum. And then this can be split up into the perpendicular and parallel components of the motion. This is really useful for part one of the lab. And then for both parts, use Newton's universal law of gravitation, says that the force of gravity is equal to this. And then for the second part, also use the velocity update formula, which is an application of the momentum principle, and the position update formula. So the reason that we're using these are because we're considering curving motion. That's why it's useful to split it up into perpendicular force and parallel force. We're also using this position update formula with V final instead of V average because net force is not constant. And we're using this instead of just Fg equals mg because gravitational force is acting over a relatively long distance. The main assumption that we're making is that the black hole and the planet have really large mass, so they can be treated as fixed objects. For the first part of the lab, the goal was to find the mass of a black hole by considering astronomical data. So to do this, you can use the data for velocity and position to find the net perpendicular force and the net parallel force and add them together to find the net force. After that, you can set the magnitude of the net force equals to the magnitude of the gravitational force to find the mass of the black hole. And then lastly, just averaging each mass calculation within the for loop. So what this is doing is it's finding the mass. It goes through all the steps that I just described, and it's adding it to a list each time it loops through all this code. And lastly, what this is doing is it's just averaging all the mass values calculated inside of that loop. So here are the results that were found. The mass of the black hole is found to be this really big number, 1.4 times 10 to the 34 kilograms, which makes sense. The black holes are really dense and have a lot of mass. For the second part of the code, the goal is to try to attempt to model a figure-8 orbit for a ship. And to do this, you have to first use Newton's universal law of gravitation to calculate the net force on the moon and the ship. So for instance, that's finding the net force planet on the moon, the force ship on the moon, and then finding the net force on the moon and doing the same thing for the spaceship to model the motion. After that, you update the velocity and you update the position as shown here of both objects. And lastly, the main difficult part of this code was to editing the initial ship velocity to attempt to model that figure-8 orbit. Now, in the end, it was basically impossible to obtain the figure-8 orbit, but this was a pretty interesting orbit that was created using these initial conditions. So minus 24,000 and 24,500 meters per second for the ship. So the main source of error was assuming that the black hole in the first part and the planet in the second part were fixed objects. They also experience gravitational attraction from, for instance, the star in both systems. Additionally, there's other forces acting on the objects. Like another example could be like I myself am exerting a gravitational force on our own star. But that isn't something that was typically taken into account in these models because it's a very negligible force. It's very small in magnitude relative to the other forces at play. So it's also worth noting that the net force and the rate of change of momentum, even though we set them equal to each other in Newton's second law, they're not really the same exact thing. The rate of change of momentum is an observable property, while the net force is not a directly observable property, and it stems instead from the interaction between objects. That's why Newton's second law is so important, because it relates this observable motion to motion that we can't, or to properties that we can't observe between the system and surroundings. Now, for another system with a black hole star and a planet, to predict the motion, we have to consider the gravitational forces acting on each component. So the black hole on the moon, the star on the moon, the planet on the moon, and do the same thing for every system. Now, if you think about all these forces and all these crazy interaction components, it gets complex really quickly, and that's why it's really difficult to predict the motion of three objects. That's what's kind of called the three-body problem. Now, it's worth noting that there would be some stronger interactions. For instance, the objects with greater mass would contribute more dominantly because mass is proportional to gravitational force. For instance, the black hole and the star would have a really strong interaction compared to the planet and the moon. So in conclusion, For part one, it was shown that astronomical data can be used to determine other properties that are difficult to measure, and this kind of goes through the steps that we used to do that to find the mass. Uh, and for the second part, it's really challenging to find a stable eight-figure orb because small changes in initial velocity drastically change the overall motion. Um, and overall, we're just using Newton's second law of gravitation and combining the computational model to analyze a system that is otherwise impossible to recreate in experimental settings. Thank you.